Hi, I'm Josh Lovell, Product Line Manager for Teledyne LABS Pharmaceutical R&D Products. Thanks for joining our regular chromatography webinar series. Today's topic is focused on purification of peptides and nucleotides with the ACCUPrep HP150 and PurIon mass spectrometer. As a reminder, if you have any audio-video issues, please exit the webinar and rejoin. This usually resolves the issue. If you have any questions during the webinar, please type them into the questions box. Some questions will be answered at the end of the webinar, while others will be followed up with after the webinar. The webinar will be recorded and made available for future viewing. Today, we are excited to introduce one of our Teledyne LABS in-house application specialists, Jack Silver. Jack is one of several application experts that we have at Teledyne LABS to help customers determine the best route to a successful separation. For any of your tough separation questions, please reach out to any of our experts with your questions. At this point, it's my pleasure to hand it over to Jack.
Hello, and thank you for your time today. Although this webinar uses the ACCUPrep HPLC, there will be many topics that will be useful to anyone purifying peptides and oligonucleotides. We will talk about multiply charged molecules and how we can use them to distinguish the desired compound from impurities. Next, there will be a discussion of a new feature that helps keep your mass spectrometer clean. Although mass spectrometers are useful for purifying peptides and oligonucleotides, these detectors have limitations. We will show how to schedule automatic runs on the ACCUPrep and the use of a large sample load pump that you can use to load dilute samples or use for desalting. Stacked injections are useful for large molecules as well as chiral, and we'll finish off with a discussion and overview of proper pH control to maximize recovery. The ion finder now makes it easier to see multiply charged ions. Many biomolecules have a mass technically larger than the PurIon can directly detect. However, these compounds are generally multiply charged, so their mass-to-charge ratio folds into the range of our mass spectrometers. Some large molecules may not show a molecular ion peak, as the example above, which has a molecular weight of 1,635 Daltons, so the multiply charged ions are the only detection available. The PurIon L is the best mass spectrometer for these compounds because of the detection range of up to 2,000 Daltons allows detection of more ions and larger compounds. Example compounds that have been run include oligonucleotides such as small interfering RNA and various peptides. The ion finder looks for the most intense peaks displayed on the screen. The 10 most intense peaks are labeled, and so you use the modified view to change the mass range so that the ion finder can display the most intense peaks within that range. Large molecules usually contain a natural isotopic abundance within a single molecule. For these compounds, enter the average mass into the ion finder. Smaller molecules should use the exact mass, which is reported by most chemistry drawing software. Different isotopes and rounding cause some of the ions to show up as two adjacent masses in the ion finder. For the most sensitivity, select the most intense peaks. The masses seen from a multiply charged compound are unique to a molecule. The peaks at a lower m/z are impurities in this particular example. We know this because they did not fit the pattern for multiply charged peptides for the desired compound, and so they weren't flagged by the ion finder. They are probably another peptide impurity. These two new features are displayed on the same screen, so I will cover both the asymmetric threshold and setting the time window for mass spectrometer detection. The first item we will discuss is the MS detection start and end. This causes the MRA valve to operate during the window defined in the start and end times. The benefit of this feature is that injection solvents are not sent to the mass spectrometer, such as DMSO, DMF, and buffers used in a previous purification step. Compounds known to be impurities can also be excluded, such as column wash steps at the end of a purification. The mass spectrometer MRA valve is turned on after the injection peak as shown in the arrows in the upper chromatogram. And then they are turned off after the focus gradient so that the impurities eluting during the column wash are not sent to the mass spectrometer. This keeps the mass spectrometer cleaner and maintains its sensitivity. Mass spectrometer peaks often tail beyond the UV, causing collection of many fractions that contain very little compound. An asymmetric threshold reduces collection due to this tailing. Mass spectrometers are noisy detectors, so the starting threshold is set to a multiple of the noise. The ending threshold is set as a function of the peak height so that small peaks can also be properly collected. In the top chromatogram, the tailing caused collection from the first peak into the second, and the second peak tailing caused fraction collection long after most of the peak has eluted. A 20% end threshold looks appropriate for the purification and allows complete separation of the compounds and eliminated collection of the tailing. Purifying peptides and nucleotides with a mass spectrometer is different from purifying small molecules. Peptides and nucleotides are larger, so more massive sample is needed for the same number of molecules. Here's a customer sample of an oligotide. 20 nanomoles was injected onto a 20 millimeter column. This is about 0.26 milligrams. The peak was 3 minutes wide, so it eluted in 30 to 45 minutes of solvent. This makes a concentration of 0.6 nanomolar solution. The sample is further diluted by the mass spectrometer split ratio that was 1,000 to 1. Also run as negative ionization, sucrose was directly injected, and about 3.6 thousand nanomolar per liter concentration was determined to be the limit of detection. Most small molecules are run at a much higher concentration, so at 0.26 milligrams, sucrose is 253 nanomoles per liter if it came out in the same fashion, which is 10 times the number of molecules. Another factor that affects collection is the molecule size. The length of the peptide or oligonucleotides determines what charges we can detect. There are only a number of residues that can take a charge, and due to coulombic interaction, you want about 3 residues between charges. So the maximum number of charges is roughly the number of bases divided by 3, and we typically don't see all of them. In this particular example, note that many of the possibilities are above 2000 Daltons and so won't be detected if your mass spectrometer has a limit of 2000 Daltons. Also, because this oligo had 21 residues, minus 7 charge is about the most that we could expect, so we might expect 1 peak from that. Furthermore, the intensity of a large molecule gets diluted because of these multiply charged ions and also due to fragmentations. As we alluded to earlier, some compounds are detected as multiple ions, and to simplify the math, let's assume that there is an equal chance that each ion can occur in the image at right. So in this example, 5 times as many molecules are needed to see the mass spec as compared for a small molecule, where every molecule shows up as a single peak, and therefore the limit of detection is larger for multiply charged molecules. While oligonucleotides have decreased detection with mass spectrometers, they were more easily detected with UV light because each base absorbs light pretty close to 280 nanometers. This example has 4 chromophores to absorb light and so acts as 4 times as concentrated as a single base that is isolated, or that's 4 times as concentrated in terms of the concentration in terms of moles. A new feature is scheduled operations. This allows certain operations to be run periodically. So some of these might be a routine operation such as cleaning the column at the end of the day, or perhaps periodically running a test chromatogram to make sure the columns are still running very well. There are many benefits to this feature. You can wash the columns at the end of the day, and this will remove buffers and modifiers and improve the column life, especially if you're using silica-based columns. You can periodically run reference compounds to verify the correct retention time. If the system is running samples at the time that the scheduled operation is supposed to occur, the scheduled operations will be appended to the current sample queue, so it will be run. And the operations to be run are saved as a queue file, so all of the columns can be washed or tested one after the other. The queue files are created in one of the queue screens and saved to the system. The large sample load pump is very useful for working with biomolecules. It can be used to load dilute samples. The sample load pump is more automated, so all loading operations are run from the ACCQPrep screen. The pump is chosen via the sample type drop-down, and the flow rate and pumping volume are set on the HPLC. The HPLC pumps can be run at the same time to potentially prevent phase collapse when loading aqueous samples if some strong solvent needs to be pumped. And the screen will appear, which allows the baseline to be observed. This allows the chemist to stop loading after the sample saturates the column. This feature is used for desalting or changing a counterion. So if you want to change from, say, a chloride to, I don't know, an acetate salt, you can do that operation now. When the large sample load pump is used, the run report also shows the absorbance trace during the time the sample is loaded. This run is from a peptide stacked injection run in 50 millimolar ammonium formate. I used the newly introduced EcoDist hydrogen roto-evaporated to remove the methanol and so dissolved the peptide in a weak solvent that concentrated the peptide at the head of a column. Note that I'm using column volumes since any changes in the loading or wash will be visible in a minimum of 1 column volume. A column volume is analogous to the void volume and is commonly used for flash chromatography. Another use is to remove buffers from samples purified by, say, ion exchange, and then you can remove the buffers and then elute the peptide. Stacked injections are new to the ACCQPrep HPLC system. Use this for chiral and achiral purifications. Stacked injections are useful for purifying a large amount of closely eluting compound. Stacked injections save time and solvent because the equilibration time and the delay time are used for the purification after the first injection to purify more sample. We can do stacked injections very easily, and they can be set up with as little as 2 injections. The ease of use allows improved time saving with fewer test injections to prepare the stacked injection. The first step is to create the isocratic method. The focus gradient generator works very well for this purpose. The focus gradient generator can create an isocratic run from a scouting run. Stacked injections need to be run isocratically. Compounds eluting very early or late compared to the desired compounds will increase the cycle time or appear as ghost peaks that contaminate the purified compounds. The scouting runs can use any injection option available on the system. Stacked injections use the auto-injector, not the auto-sampler. The auto-sampler is disconnected and the auto-injector probe is connected to the injection valve. If a user has only an auto-injector, that probe is used. The system will prompt the user to set up the injection probe and will prompt the user to change or replace the autosampler probe when it is needed. Collect the peaks during the run. The post-separation pause will work even if a single injection is used. If the purification is good, the stacked injection can be run. Note that the focus gradient generator adds a column wash step. Remove those solvent gradient segments with the method editor prior to the run. The stacked injection button is used to configure stacked injections. If desired, the user can adjust the solvent composition and loading to optimize the chromatography before starting the stacked injection. Collecting the fractions allows Peak Track to configure initial time windows. Time windows can be set manually if needed. The time windows can be adjusted and unwanted time windows can be removed. The simulated chromatogram is based on the last isocratic run, so it is based on real data. Fraction pooling causes the same peak from different injections to be collected in the same container. To reduce the number of fractions, use the largest containers possible to reduce the total number of containers used. Each time a user needs to combine fractions creates a possibility for error by combining the wrong fractions. Use the Show Single Injection button to display a single injection. This allows time windows to be adjusted more easily. The table here explains how the Collect Peaks and Collect All work within the same time window when fraction pooling is turned on and off. Turn off the single injection display to visually adjust the cycle time. The total sample can be adjusted. The injection volume should not be changed as this affects the peak width. Pressing the OK button shows the run requirement screen. Check that the solvent bottles are filled and the waste container is empty. Make sure that the waste container is large enough and there are enough fraction containers for the run. The time windows can be adjusted during the run if needed. The colors show time windows from the same injection, while the cross-hatching are time windows used within a single injection. The window scrolls to keep the injections visible on the screen, and the Modify View button can be used to set how many injections are visible on the screen. Doing a scouting gradient provides a lot of information. Peak Track can calculate a focused or isocratic gradient method. The peak shape can suggest if the pH and buffering is good for elution, and the resolution between peaks can suggest sample loading. More resolution implies greater loading. Ionization settings can be used to detect the detection on the mass spectrometer. The electrospray interface voltage can be adjusted as well as the probe temperature. Thermally labile compounds can be run at a lower temperature to reduce fragmentation. Oligonucleotides can run at a lower temperature and voltage to improve ionization. For this peptide, note the span setting is set to 0 and the base peak is about 1.8 e to the 7 count. Changing the span to 10 volts increased the intensity from 1.8 to 2.1 e to 7, a 50% increase in sensitivity. The offset voltage tends to affect smaller molecules to a greater extent, while larger molecules show more sensitivity to span adjustments. The scouting gradient gives a quick look about the compound purity. This peptide has several impurities that elute later, which will cause long cycle times. This peptide should be pre-purified with a gradient on a flash system or an HPLC. Because the impurities are generally far from the peptide, the column can be heavily loaded to reduce the number of runs needed to remove those impurities. This peptide has several multiply charged ions, making identification of the peptide easy. However, there is a shoulder ahead of the main peak. The different traces show that it is the same compound as that in the main peak. This suggests that the compound should be run at a different pH. However, cyclic peptides will also show multiple peaks for the same pure compound due to multiple stable conformers that can naturally be resolved. In the next section, we'll look at a real customer peptide example. When customer shared the molecular weight, the mass spectrometer signal was optimized as described earlier, and the ion finder was used to find and select the peaks representing the double and triply charged ions. A scouting run suggests that this peptide is a good candidate for stacked injections. All of the impurities are close to the desired compound. Although visible as shoulders on the main peak, they will be resolved using an isocratic method. This peptide was soluble in water with only a little methanol, so no DMSO was needed. This is very good because DMSO shows up as an early eluting peak and so would increase the cycle time. If you need to dissolve your peptide in DMSO, it might not be a good candidate for stacked injections. A small injection was run here, only 200 microliters. The main peak elutes a little later than expected, but it is in the range of the isocratic method. However, several peaks with the same mass-to-charge ratio were detected. This suggested that the pH was incorrect. The sample was run in ammonium formate buffer at pH 3.5. The customer shared the peptide sequence with me. I used a nice tool on the Bachem website to calculate the peptide's pI. The pI is the pH where the molecule has a net neutral charge. This does not mean that the molecule is not ionized. It means only that all of the charges balance out. The method was buffered at pH 3.5, but the pH was 3.9. It is best to be at least 1 pH unit away from the pI to maintain a stable charge state. Most C18 columns are silica-based and so shouldn't be run at a pH above 7 to 7.5 because silica dissolves in basic polar solvents. A pH close to 7 looks like it would work looking at this graph here. A new scouting run with ammonium carbonate was run. This buffers at about pH 6.9. A new scouting gradient was run with the new buffer, which created a new isocratic method, and now the peptide elutes as a single peak. A stacked injection was run, and it needed only 2/3 of the time compared to multiple single injections, even if I shorten the equilibration time for each injection. And also it needed 2/3 the solvent. There was less waste too because the delay time was filled with sample. Here is an example using a smaller peptide, EGFR. The first run uses the common water acetyl nitro modified with 0.1% TFA, that is trifluoroacetic acid. The calculated gradient in the center shows a late elution. A slight adjustment to the focus gradient causes a nice elution. The start and end of the focus gradient were increased by 5%. The mass spectrometer trace suggests that the same compound is in multiple peaks. This shows that the compound has multiple ionized states that are stable under these conditions, each with its own polarity and its own retention time. This is because TFA is not a buffer in preparative HPLC. TFA is about 6 millimole concentration at about 0.1%. For this run, 50 milligrams of peptide was injected with a mass of 1,635 grams per mole, which is 0.03 millimoles, which doesn't sound like very much. This is, however, ideally eluting in the volume of about 20 mils or 1 fraction collection tube. So the concentration within the peak is closer to about 2 millimolar and is about 1/3 the concentration of the modifier, enough to deplete the slight buffering capacity of TFA. The extra peaks represent lost compound if the peptide was purified only with UV detection. Analytical HPLC injections contain so little material that the TFA can control the ionization and the pH is not affected. So let's try a buffer, but now I need to make some changes to my solvent system. Ammonium acetate is soluble in the presence of methanol, but not acetonitrile. The focus gradient generator worked in this run with the gradient modifications needed, with no gradient modifications needed. However, we still see multiple peaks in the UV and mass spectrometer. The next thing we will try is a lower pH, since this peptide has a pI of 4.5. This is the pH where the positive and negative charges on the peptide balance out, so it has a net charge of 0. I like to be more than 1 pH unit from the pI because small changes in pH can cause the peptide to have something other than a net 0 charge, causing shifts in retention time. To lower the pH, I change to ammonium formate, which buffers at about pH 3.5. The peptide elutes as a single peak now and is mostly resolved from impurities. This purification would give both good purity and recovery. I used ammonium and acetate and ammonium formate because they are volatile and can be used with the mass spectrometer. Since this is a preparative LC system, only a tiny portion of the flow, microliters at any one time, gets diverted to the mass spectrometer, so I could use 50 millimole buffer. The buffer gets diluted by the carrier solvent and delivers the sample to the mass spectrometer. And again, these are volatile buffers, so they don't clog up the mass spectrometer. Here is a list of volatile buffers which can be used to purify peptides and oligonucleotides. One thing to note is that for some samples you might need to use nuclease-free water. You probably want to use DNase or RNase ZAP to help keep your oligos from degrading. And thank you for attending our webinar. Visit Teledyne For more information, visit TeledyneLabs.com. And you may also find us on social media with the links listed above in this slide. Now we are ready to take questions. The first question is the M plus 2H and M plus 3H and you can also find us on various social media with the links listed in this slide. Now we can open it up to questions. The first question is on slide 6. The M plus 2H over 2 and M plus 3H over 3 were shown. What do these mean for my ions and compound? That's a good question. The M plus 2H over 2 and M plus 3H over 3 are multiply charged ions that we can detect. They help to uniquely identify the compound. Deletions are the most common impurities where bases are missing, and they will have a different set of multiply charged ions that do not match the desired compound, and so they will not be picked up by the ion finder. The next question is, can I run stacked injections with mass spec detection? If so, how can I keep the mass spectrometer clean? You can do stacked injections with the mass spectrometer. However, to keep the mass spec cleaner, use the minimum loading option that detects the compound. This sends less material to the mass spectrometer. I have a very precious sample. How can I improve recovery with mass spectrometer detection? This question has a couple of aspects. The starting and ending thresholds can be set lower. In addition, the mass spectrometer can detect peaks belonging to your compounds that are separate from the main peak due to pH or conformation issues, as we showed. So you use the mass spectrometer and you can lower the threshold to collect more sample. And in addition, the mass spectrometer can see if your compound is eluting in other peaks other than what is expected. And I thank you for your questions. And if you have more questions, you may email me at jack.silver@teledyne.com. Again, jack.silver@teledyne.com.